Hi everyone. So in this video, we're going to be talking about the average value of a function. So you might notice that we're going a little bit out of order. Basically, just after teaching this class the last time, I realized that I think this section fits a little bit better now rather than later. So we're going to be doing 6.5 in this video, and then in the next video, we're going to go back to 6.1. So average value of a function is basically just, if you have a function and you're focusing on one interval, one set of x values, the average value of the function is the average height that that function achieves on that interval. So we're going to start with an example as a way to kind of motivate the formula for average value, and then we'll get to stating what the formula actually is, and then we'll do some examples, and we'll see that the methods that we learned in the previous video, so stuff like substitution, that's going to come up here as well. So all of the different methods we have for evaluating integrals, those could come up in this context and in future contexts as well. Okay, so I want to start with an example. So let's say, suppose that you have a constant function. So f of x is a constant function, meaning it's just a horizontal line. But let's say that for whatever reason, we don't actually know what height that horizontal line is at. So we have some kind of a constant function, and I'll just kind of sketch something in here, and we have no idea, what that the height of that function actually is. So I'm going to write that down. So we don't know the height of f of x. We don't know, what number it's actually equal to. But let's say that for some reason, somehow, we know that the integral from 1 to 5 of this function is equal to 12. So how could we find the height? Well, let's think about what we're talking about here. If we say the integral from 1 to 5 of this function is 12, what does that actually mean? Well, that means that if we go in between 1 and 5 and sketch this rectangle, if the integral from 1 to 5 of this function is equal to 12, that means that the area of this rectangle is 12. So how do you find, in general, not using calculus, how do you find the area of a rectangle? Well, it's base times height, right? So here we have a base, and the base is equal to 4, right? And how would you get 4? Well, you could just count it, or you could do 5 minus 1. So if you subtract the two endpoints, that tells you how long that base actually is. So our base is 4. And then our height, that's what we don't know, right? The height is question mark. So how could we actually go about finding the height? Well, we know that area is equal to base times height. And so if the area is 12 and the base is 4, well, that would tell us that the height is equal to 3. So, this is not a question that we would need calculus to answer, but I want to kind of rephrase what we did here in terms of calculus, because the kind of calculus format of it is what we will then go ahead and use in the future. So basically what we just did here is we took the integral, actually I'll say it this way, we found the height by taking the integral from 1 to 5 of our function and dividing it by 4, right? Because 4 was the base. And this integral here was the area, right? So the integral from 1 to 5 of our function, that represents the area. the 4 represents the base, and so if we divide them, we get the height. And another way of writing this would be taking the integral and multiplying it by 1 over 4. And again, where did that 1 over 4 come from? It came from subtracting the two ends of our interval. So the height was 1 over 5 minus 1 times the integral from 1 to 5 of f of x dx. So again, you would, probably not write it out that way because you could just kind of look at the picture, but it turns out that what I wrote down here with the integral, that's actually the average value formula. So the idea, and we'll see that in an example in a moment, is that even if your function is not a constant, you're not finding the height in the same way that you are in this one, because in this one you're just finding like there's only one height, right? And you're finding exactly what that height is. But what we'll see in a moment is that if you're doing the same procedure with a function that varies, you're basically finding what is the average height. You're kind of imagining, okay, like if I kind of imagine that this area was a rectangle, what is the base and what is the area? And if I do the area divided by the base, that will give me then the average height of the function. So we can use this same idea to find not like the exact height, but the average height of any function f of x. And what we're going to call it, instead of calling it the average height, we're going to call it the average value of the function. Because when you're talking about a function, when you talk about the value of the function, you're always referring to the outputs or the y values, which is the same thing as the height, right? So we'll call this the average value of the function. Okay, so now let's write down the formula and we'll get into an example right away. So the average value formula, let me put it this way. So the average value of a function f of x on an interval. So we're always looking at an interval when we're talking about an average value, because otherwise you would have infinitely much of the graph and it just doesn't really make sense. You can't really do a calculation like this. So the abbreviation that we'll use for this is f with then like a little subscript that says AVE. I always feel funny when I write this down because I feel like it looks like fave, but it's just f average. And so the formula is going to be 1 over b minus a times the integral from a to b of f of x dx. So again, where does this come from? Just like if you ever are having trouble remembering this formula, go back to this idea of a rectangle and think about, well, if you have a rectangle and you're looking for the height, you do the area divided by the base. And the area is this part. And the dividing by the base, well, that's this part. And so that's basically what we're doing. We're just doing it in a case where now we don't have a rectangle anymore. Okay, so let's look at an example. So we're going to start with a really simple example just because I think it's nice to kind of illustrate visually what's going on, and then we'll get into some slightly trickier examples. Okay, so let's say that we wanted to find the average value of f of x is equal to x squared on the interval from 0 to 3. Okay, so how do we do this? Well, we want to take the integral from 0 to 3 of x squared, and that will give us the total area. So that will give us this area. And then we're going to divide that by 3, and that will tell us on average what the height is of this portion of the graph. So we're going to multiply this by 1 over 3 minus 0, which is just 1/3. So we've done this one in the past, but let's just do it again. So the integral from 0 to 3 of x squared, that means that we have the antiderivative being x cubed over 3. And I'm just going to leave this 1/3 on the outside of the integral, and we can multiply it in at the end. And then we're evaluating at 3 and at 0. So we're going to get 1/3 times, so if we plug in 3, we get 27 over 3, which is 9. And if we plug in 0, we just get 0. And so overall, we're going to get 1/3 of 9, which is 3. So that is our average value. So kind of visually, the way that you can understand what's going on here is that basically, if the average value of this function is 3, that means that if we were to draw a box at a height of 3, like this, the area of this purple rectangle is actually the same as the area of the blue area, right? Because basically what we're saying here is that if you imagined this function, f of x is equal to x squared, if you imagined it as a constant function, if you kind of smushed it down so that it became a constant function, in order for it to have that same area under its graph, it would then need to be at a height of 3. And so therefore, the blue area is the same as the purple area. So I'll write that down as kind of a side note. So note, this means that the blue area is equal to the purple area. So that's kind of always the case, and that's something I'll ask you to do on the worksheet for today as well. You know, when you find the average value, also draw that rectangle to kind of give you a visual of, if that function was a constant function, what would it look like in order to have to achieve that same area? Okay, so there's one more part of this, this whole average value idea that I want to get out, and we'll look at it with respect to this answer, and then we'll get into some other examples. So this is something that's called the mean value theorem for integrals. So basically, the mean value theorem for integrals says that if your function is continuous, so if it's a nice function, doesn't have any weird jumps or gaps in it, that whatever the average value is, your function has to at some point actually pass through that average value. So let me write that down, and then we'll see how that plays out in the previous example. So if f of x is continuous on AB, then f of x must achieve its average value. And what I mean by that is actually go through that height. It must have at least one point where it actually has the same height as its average value at some point between A and B. And so the more kind of formal way of saying that is that, in other words, there exists some x value I'll just say some number c, which lies in the interval from A to B, such that f of c is the same as the average value of the function, which I'll just write out again what that was. So that was 1 over b minus a times the integral from A to B of f of x dx. So one kind of extra thing that we might do in some of these problems is, in addition to finding the average value, find the x value, the point in your interval where the function actually achieves that average value. So let's go back to this function for a second. So at what point does our function f of x equals x squared actually achieve an output, a height of 3? Well, we can see it on the graph here, right? It's this point here where the line y equals 3 crosses our graph. So we can estimate that it looks like it's somewhere between 1 and 2, right? It's like a little closer to 2. How could we actually find exactly what the x value is? Well, forget about calculus for a second and just think about what we're actually trying to answer here. So if we're trying to find at what x value our function reaches a height of 3, that's the same as just solving f of x is equal to 3, right? So all we have to do to figure out what that x value is set 3 equal to x squared and solve. So I'm going to go down and do that below. So going back to our example above, find a number c on the interval from 0 to 3 such that f of x equals x squared achieves its average value, and the average value that it has to achieve was 3. So all we have to do is just set our function equal to 3. So f of x is equal to 3. And so the function was x squared, so we have x squared is equal to 3. And then we can take the square root of both sides, so we get x is equal to plus or minus square root of 3. But we're looking for a number that's specifically within the interval from 0 to 3. And so that tells us that we're going to choose the positive one. So x is equal to square root of 3 is our answer. So when you see that question being asked, find a number c, it's really not, you're not doing calculus in that part. You're just taking whatever number you got and just setting it equal to your function. And depending what kind of function you have, solving that may be easier or harder, but it's definitely not really using calculus. It's just doing algebra. Okay, so I want to get into a slightly more, first we'll do one kind of quirky example, and then we'll get into a more challenging example. And then after that, we'll also do an example that is actually like a real world application, because I think seeing how you can interpret average value in the context of an actual real world situation might really help you understand what exactly is going on here. Okay, so the next example I wanted to look at was, I basically just wanted to emphasize the fact that remember that when you're dealing with integrals, portions of a graph that lie above the x-axis are counted as positive, and portions that lie below the x-axis are counted as negative. And so even when you're finding average value, I just want to emphasize that the positivity and negativity is counted as positive and negative. So what do I mean by that? Well, let's say that you are asked to find the average value of f of x is equal to sine of x on the interval from 0 to 2 pi. So again, we can write down the formula here, but we'll see that there's actually not really too much work to do for this problem. So we would say, okay, the average value is going to be 1 over 2 pi minus 0, so 1 over 2 pi, times the integral from 0 to 2 pi of sine of x dx. And you could totally evaluate that integral, but the kind of shortcut for answering this is looking at, what is the actual area we're talking about here. So if we're talking about the integral from 0 to 2 pi, we're looking at this portion of the graph, and this is going to count as positive, right? And then we also have this portion of the graph. And this portion of the graph looks exactly like that first part, it's just negative. And so even without evaluating the integral, basically because we know that sine is a very symmetric graph that repeats itself, we know that that positive area and that negative area are equal. And so the integral from 0 to 2 pi of sine of x is actually just equal to 0. So I'll write out kind of one more step here, which is we have 1 over 2 pi times 0. And so our average value is 0. So why is that? Why does that make sense? Well, if you think about all the different heights that you get in this function, you have all these different heights here, and they're all kind of varying, right? Like some of them are shorter, some of them are taller. But then you go and you have all these, like basically the same heights, but just the negative of them. So they all kind of counteract each other and they balance out to give us a total average value of 0. And so we can answer one more question here, which is what we just answered a moment ago, which is find all values of c in the interval from 0 to 2 pi such that f of x is equal to sine of x achieves the average value And so this just means now looking at our function and finding the places where the function is equal to 0. So sine of x is equal to 0 is basically what we're trying to solve, right? So we have f of x is equal to sine of x. And we happen to have the graph right here, and we can just say, okay, well, I can see 3 places where that happens, right? At 0, at pi, and at 2 pi. And of course, there's more values, but again, we're just focusing on between 0 and 2 pi. So the answers to this would be x is equal to 0, x is equal to pi, and x is equal to 2 pi. All right, so next example we're going to look at. For this one, we're going to be finding the average value of the function is g of t is equal to t over the square root of 3 plus t squared. And we're going to be focusing on the interval from 1 to 3. Okay, so why do I say this is a trickier example? Basically, we'll see that when we go into the integral, the last couple we did, this one we could just kind of see by looking at it, and then the one before that was a very simple antiderivative. So this one's going to be a little bit more work to actually evaluate that integral. So how do we find the average value? Well, we're going to say 1 over 3 minus 1. So that's the part where we're kind of dividing by the width. And maybe let me just go in here and emphasize the part. This is really the part of the graph we're looking at here. So we have 1 over 3 minus 1 times the integral from 1 to 3 of t over the square root of 3 plus t squared dt. So how do we go about evaluating this integral? So basically, we really only have one method that can be used for things other than simple antiderivatives, right? So we have those antiderivatives that we can just know, like the reverse power rule, or if you see something that's like an inverse trig function or a trig function, or 1 over x, the antiderivative of that is ln of absolute value of x. Those are all the ones that we can just know off the top of our heads or look up. Something like this, really the only method we have is substitution. And so that's where your mind should go is, what could I do? What could I set u equal to that would allow me to then evaluate this integral? And so really, I'd say there's only kind of 2 candidates for what u could possibly be. One idea would be letting u equal this whole thing. And I'll come back and tell you why that is not the correct answer in a second. The correct substitution here is going to be to let u equal 3 plus t squared. And so how can you know that that's a good substitution to do? Well, again, there's kind of 2 things you want to check. One is, will I actually be able to evaluate this integral once I do that substitution? And then the other thing is, when I take the derivative of what I'm setting u equal to, does something similar to that derivative appear in my integral? And so if we let u equal 3 plus t squared, so if we let u equal 3 plus t squared, well then when we take the derivative, we get du is equal to 2t dt. And that's a good sign because notice that we have a t times dt. And so 2t dt is very, very close. Basically, we're just going to end up dividing by 2. There's going to be an extra factor of 2 in the denominator. And to really see how it works, what you can do is, again, solve this for dt, and then that will tell you exactly what you need to put in instead of dt. So if we solve this for dt, we get du over 2t is equal to dt. And so basically what will happen is when we make this substitution, the t's will cancel out. And so we'll be left with something we know how to integrate, right? Because 1 over square root of u is something that we can do using the reverse power rule. So why would it not have worked to make u equal to this whole thing, to square root of 3 plus t squared? Well, then the derivative of that would be a lot more complicated, right? If you wanted to take the derivative of the square root of 3 plus t squared, you would have to use the chain rule, and that would introduce things that would not be able to cancel out with the t entirely. So it's really, it's definitely trial and error is fine. So I recommend trying it and see for yourself why it doesn't work. So one thing I want to emphasize here that I could see how it could be confusing is that we're about to go do this substitution. We're not actually going to change this part. And I know maybe it kind of feels like we should, right? Because this 3 and this 1, those were actually t values, and we're trying to switch everything to u. But basically, because this is outside of the integral, it's just a number. And so we actually shouldn't make any changes to that. Think of it as, it's a number, it's just a number that we're multiplying the integral by. Basically, it's because it's not inside the integral, it's not going to be affected by our substitution. Okay, so let's go in and do this substitution and see how things play out. So we're still going to have this extra factor of 1/2 outside. And then we're going to have the integral, and remember we have to change the bounds, so I'll do that in a second, of t over the square root of u. So we're replacing 3 plus t squared with u, and then we're replacing dt with du over 2t. And so that will enable this t and this t to cancel out. So what are the new bounds going to be? Well, remember that the original bounds were t values, right? So you can think of this as t equals 1 and t equals 3. So to find the new bounds, we're just using this equation here. So the new bounds will be, the first one will be u is equal to 3 plus 1 squared. So that gives us 4. Sorry, I wanted to use this color. And then the upper bound is going to be if we plug in 3, so plug in this value for t, and we get 3 plus 3 squared, which is 12. And so this is our new integral. So now we're just integrating the integral from 4 to 12 of, so this is 1 over square root of u. Another way to write that would be u to the negative 1/2 du. So now we can do our antiderivative, right? So the antiderivative of u to the negative 1/2 would be, the new exponent will be 1/2, right? Because we add 1, and then we take the reciprocal of that, which is 2 over 1. And so this 1/2 is actually going to cancel out. And okay, so from here, where do we go? Oh, and actually, sorry, I just realized I forgot something. I was looking at my notes and I was like, that's not the same. Sorry, my bad. So what I realized that I forgot is about this extra 2. Sorry about that. I hope that didn't confuse you. So we had this extra factor of 2 that we can then pull outside of our integral. So anytime you're doing a substitution, if you have an extra factor of 2 or whatever number, you can just pull that outside of the integral. And I generally prefer to do that because it will just make things a little easier when you're actually evaluating the integral. So basically we had 1 over 2, so we can pull that out, and that gives us now 1 over 4. Okay, so back to what I said before. So we had u to the negative 1/2 du. Okay, so like I said, our new exponent is 1/2, and then we're multiplying by 2 over 1, and then we're evaluating that at 12 and at 4. And if you wanted at this point, actually, you could pull out this 2 over 1 as well, but I'm just going to leave it on the inside. It doesn't really make anything harder, so I'll just leave it there. So the first part is we're plugging in 12. So we have 2 times 12 to the 1/2, or 2 times the square root of 12. And then we have 2 times 4 to the 1/2, or 2 times the square root of 4. So this is going to be 1/4 times, now we have, oops, I don't know why I wrote 2. So square root of 12, we can rewrite that as 2 root 3, right? Because square root of 12 is square root of 4 times square root of 3. And then 2 times the square root of 4 is just equal to 4, because it's 2 times 2. So this is 1/4 now times 4 root 3 minus 4. And so this can be simplified to square root of 3 minus 1. And that is approximately equal to, by the way, 0.732. So basically, if we look at our picture here, so if we go to a height of approximately 0.732, so that would probably be somewhere around here. And I think I didn't draw that very well, so let me try to do that a little better. Maybe it's more like here. This rectangle that I drew from 1 to 3 would have the same area as the original shape of the graph in blue. And how would we find exactly where, like, so say on this question, it also asked us, find a value of C that has that height. So you actually could use algebra to solve this. I'm not going to go through it because it's a little tedious. It's probably harder than something I would actually give you on a test or anything. But if you set t over the square root of 3 plus t squared equal to square root of 3 minus 1, then that would totally work. You could definitely solve that for t. It would just be kind of a little bit annoying of algebra. But another way that you could at least get an approximation for where are the values or value where this function reaches that height is you can use Desmos. And so I just want to quickly show you how you can do that. Okay, so if you have the original function graphed, so here I have g of x is equal to, I wrote it with x instead of t, x over the square root of 3 plus x squared. Now if I go in and I just make a horizontal line, so I just said y is equal to square root of 3 minus 1, which was the average value we found. Then if I type that in and put it on as a horizontal line, then Desmos actually will show you exactly where those 2 points intersect. So they intersect at approximately 1.861. So that would be approximately the C value or the X value where our function reaches a height that is equal to the average value. So I just wanted to show that too, because I don't know if everyone's aware of that. It's a nice trick on Desmos that, yeah, basically, if you don't have this horizontal line, you can drag along here and kind of try to figure out, but as soon as you put in a horizontal line at a particular height, it will exactly show you the point where they intersect. So it's kind of a nice shortcut. So the last thing we're going to do is look at kind of an application so that you can get maybe a little bit more intuition for what it really means to find the average value of a function. So let's say that we have a particular city and we have a function that models the temperature of that city after a certain number of hours. So suppose that the temperature in degrees Fahrenheit of a particular city, t hours after noon. So t equals 0 will be noon, t equals 1 will be 1 p.m., and so on, is modeled by the following function. So f of t is equal to 9 times cosine of t over 4 plus 18 times sine of t over 4 plus 50. So the question we're going to answer is we're going to find the average temperature from noon to midnight. Okay, so let's start by kind of rephrasing this question so that it sounds more like the problems we were working on earlier. So what do I mean by that? Well, if we're finding the average temperature, that's the same thing as finding the average value of the temperature function, right? So another way of phrasing this question would be that we're trying to find the average value. So in other words, we're finding the average value of the function f of t. And what interval are we focusing on? Well, we're focusing on the interval from 0 to 12, right? Because that is starting at 0 hours after noon, which is noon, and then going all the way to 12 hours after noon, which is midnight. And so the formula we're working with here is going to be 1 over 12 minus 0 times the integral from 0 to 12 of our function. So we had, again, 9 times cosine of t over 4 plus 18 times sine of t over 4 plus 50 dt. So how are we going to evaluate this integral? Well, this is another u substitution problem. So this is one of the ones where you don't necessarily have to use substitution. You might be able to kind of figure it out in your head. Basically, because the substitution we're going to be making is going to be kind of a simpler one than on the earlier problem, we're going to just substitute out this t over 4, right? We're going to replace t over 4 with u. And what we'll see is that the derivative of that substitution is just going to be a multiple of the derivative of t over 4. So basically, this is one of the ones where, I think some students like to actually explicitly write out the substitution. Some people like to kind of just do it in their head and kind of think of this idea that we talked about at the beginning of the substitution about kind of counteracting. It's this idea of like counteracting the chain rule. So I'm going to do it with the actual substitution, but I just wanted to kind of mention that in case you're someone who likes to do it the other way. So we're going to let u equal t over 4. And so what is the derivative? What is du going to be? Well, t over 4 is the same thing as 1/4 times t, right? So the derivative of that is going to be 1/4, and then we put the dt on this side. So du is 1/4 dt. And so another way of writing that would be to say that 4 times du is equal to dt. And so we're going to replace dt with 4 du, and then replace t over 4 with u. So our new setup here is going to be 1 over 12 times the integral. So what are the new bounds going to be? Well, the substitution is that u is equal to t over 4. So we just have to divide each of these bounds by 4. So 0 over 4 is 0. 12 over 4 is going to be 3. And then we have 9 times cosine of u plus 18 times sine of u plus 50. And then we're multiplying that now with 4 times du. And so I'm just going to do one thing before we start to integrate this, which is I'm just going to take this 4 and bring it to the outside of the integral. So we're going to end up with 4 over 12, which is the same as 1/3. So we have 1/3 times the integral from 0 to 3 of 9 times cosine of u plus 18 times sine of u plus 50 du. Okay, so now we're ready to start finding the antiderivatives and get ready to actually plug some stuff in. So we have 1/3 times, so the antiderivative of 9 times cosine of u would be 9 times sine of u. And then the antiderivative of 18 times sine of u would be negative 18 times cosine of u. And then the antiderivative of 50 is going to be 50 times times u. And then we're evaluating at 3 and at 0. So let's write this out. So we're going to have 9 times sine, and actually I'm going to scooch over because I think this might be a big expression. Just want to leave plenty of space. So we have 1/3 times 9 times sine of 3, and that's something we're going to have to type into a calculator, right? Because that's not like a nice angle. Minus 18 times cosine of 3, plus 50 times 3, which is 150. And then from that, we're going to subtract 9 times sine of 0, minus 18 times cosine of 0, plus 50 times 0, which is just going to be 0. Okay, so I'm going to type some of this stuff into a calculator. So I'm just going to type in all at once 9 times sine of 3 minus 18 times cosine of 3 plus 150 so that I'm not like rounding more than I have to. So 9 times sine of 3 minus 18 times cosine of 3 plus 150 is equal to 169.09 approximately. I'll put in a approximate. And then what is 9 times sine of 0? Well, that's just 0. And then what is cosine of 0? That's 1. So this is going to become plus 18, right? Because we have a minus, and then we have another minus. So here and here, that becomes a plus, and then cosine of 0 is 1, so we have plus 18. So what's this going to give us? Well, this is approximately equal to 62.36. So that is our average temperature over the time period. So that looks like something like this. So I'm just going to kind of draw a line in here. So 62.36, that's going to be somewhere, and I'll pull it up on Desmos in a second so you can see the actual thing. But basically we're saying somewhere around here is the average temperature. And so it looks like there's 2 different times where the actual temperature matches the average temperature. So that's the next part I want to answer. And like I said, we'll use Desmos to like really do that. But so the question we want to answer now is, at what times does the actual temperature agree with the average temperature? And so really this is equivalent to doing that second part that we've done on the other ones. We're basically looking for a value, an x value in our interval that agrees with the average. And so what we're really doing here is we're solving f of t is equal to 62.36. And this is one which actually we're not going to solve this. It's definitely not an easy one to solve because we would have 9 times cosine of t over 4 plus 18 times sine of t over 4 plus 50 is equal to that. That's just not really something that, that we have the tools to solve. So instead what we're going to do is we're going to solve by graphing. And so what I mean by that is basically the same thing that we did in the previous question. So we're going to look at the graph of our temperature function. And so here I have the temperature function graphed in black. And then I have the height of 62.36 graphed in blue. And so we can see that they intersect at approximately 0.791 hours and 8.066. So let me write those down. So 0.791 and 8.066. So what does that mean in terms of like kind of going back to our problem? That means that we have a temperature that's equal to the average temperature at approximately, sometime between noon and 1, right? Like a little bit closer to 1 p.m. or 1 p.m. And then the second time that the temperature is equal to the average would be just a little bit after 8 p.m., right? Because that would be 8 hours after noon. All right, so that's it for this video. Like I said, there's a worksheet that will do some practice, both with the kind of more straightforward, just working with functions, but then also with an application like this, which I think is just really important for really kind of being able to make sense of what it is that you're actually doing with these types of problems. All right, I will see you in the next video.